Let us move on to another permutation test. Now we're going to check other attributes. We can use the same method to compare other attributes of the smokers and non-smokers, such as their ages. The histogram of ages of two groups show that in the sample, the mothers who smoke tend to be younger. In our histogram, we want to visualize the maternal age and both maternal smokers and non-smokers. So take a look at the overlying visualization here. As you can see, for the yellow graph, which is related to smokers, we see the majority of the data are located on the left-hand side. And here you have a frequency for the non-smokers, which tend to be a little bit shifted to the right-hand side. But we need to do a little bit of algebra and calculate the numerical values. I'm going to show that the observed difference between the average age is about negative 0.8 years. It means that smokers on average are younger than non-smokers. Let's rewrite the code that we use for the birth weights so that it now compares the ages of smokers and non-smokers. We are defining function, difference of means, and now we're passing two arguments, the table and group label. It basically calculates the difference in means between two groups based on given column, such as, for example, maternal smoker. Now, if you run the line of code, you have negative 0.8. Remember that the difference is calculated as the mean age of the smokers minus the mean age of non-smokers. So the negative sign shows that the smokers are younger on average. Is this difference due to just random chance, or does it reflect an underlying difference in the population? This is the question that we are interested in answering. As before, we can use a permutation test to answer this question. If the underlying distributions of ages in the two groups are the same, then the empirical distribution of the difference based on permutated samples will predict how the statistic should vary due to chance. Now we're going to follow the same process as in any simulation. We start by writing a function that returns one simulated value of the difference between means, and then write a for loop to simulate numerous such values and collect them in an array. So the same process, what we did so far, we're just repeating this for a new attribute. This function basically simulates one instance of difference between the mean ages of smokers and non-smokers, and after shuffling the labels. Then it randomly shuffles the maternal smoker labels while keeping the ages unchanged. This is the core of the permutation test, as it breaks any original association between smoking status and age, simulating the null hypothesis. Remember that null hypothesis says the smoking and the age are unrelated. We're going to repeat this 5,000 times. And we're going to take a look at the observed difference. The observed difference is in the tail of the empirical distribution of the differences simulated under the null hypothesis. The observed difference is going to be negative 0.8076 and the rest of the digits. Table open close parentheses dot with column basically creates a table with a single column labeled difference between group means that contains all the values in age differences that simulated 5,000 differences. Then we visualize this. In our visualization, it seems like the histogram is centered around 0, which is basically the difference between group means. But take a look at the red dot here. The empirical distribution of the simulated differences is centered roughly around 0 because the simulation is under null hypothesis, that there is no difference between the distribution of the two groups. But what about the red dot on the left-hand side? The empirical p-value of the test is the proportion of simulated differences that were equal to or less than the observed difference. This is because low values of difference favor the alternative hypothesis that the smokers were younger on average. So let's calculate our p-value. The p-value is about 0.0108. This is rather small. Compare p-value with alpha, which is 5%. You can say that, hey, since p-value is less than equals to alpha, we're going to reject the null hypothesis. The empirical p-value is around 1%, and therefore it is significant statistically. The tests support the hypothesis that the smokers were younger on average. So again, since p-value is less than equals to alpha, we're going to reject the null hypothesis that any difference is due to chance, and we're going to support the alternative hypothesis.